nozzles and orifice as flow measuring device. The mass rate of flow of fluid flowing in a pipe is frequently determined by measuring the pressure drop across a nozzle or orifice in the line. The mass rate of flow of a fluid flowing in a pipe determined by measuring the pressure drop across a nozzle or orifice in the line. As shown in the picture here. The ideal process for such a nozzle or orifice is assumed to be isentropic flow through a nozzle that has measured pressure drop from inlet to exit at a minimum cross-sectional area equals to the minimum area of the nozzle or orifice. The actual flow is related to the ideal flow by the coefficient of discharge, which is defined in the previous section. The pressure difference measured across an orifice depends on the location of the pressure taps, as indicated in the picture. The pressure difference measured across an orifice difference a nozzle or orifice in the line depends on the location of pressure tabs as indicated in this picture. Since the ideal flow is based on the measured pressure difference, it follows that the coefficient of discharge depends on the location of the pressure taps. Also, the coefficient of discharge for a sharp-edged orifice is considerably less than for a well-rounded nozzle, as shown in here and here, primarily due to the contraction of the stream, known as the vena contracta, as it follows through a sharp edge orifice. There are two approaches to determine the discharge coefficient of a nozzle or orifice. One is to follow a standard design process. There are two approaches. to determining the discharge coefficient. Discharge coefficient CD follow a standard design procedure. Such as the ones established by the American Society of Mechanical Engineering, ASME. A more accurate method is to calibrate a given nozzle or orifice and determine the discharge coefficient for a given installation by accurately measuring the actual mass rate flow. The second one is the calibrate a given nozzle or orifice and determine the discharge coefficient for a given installation by accurately measuring the mass flow. Mass flow M dot. The procedure to be followed will depend on the accuracy desired and other factors involved such as time, expense, availability of calibration facilities in a given situation. For incompressible fluid flowing through an orifice, flow, the ideal flow for a given pressure drop can be found by the procedure outlined in the previous section. Actually, it is advantageous to combine the equations 17 and 21 to give the following relation, which is valid for reversible flow. The specific value pressure between 2 points should be equals to 0. We make a simplification, we can obtain for an ideal gas, it is frequently advantageous to use the following simplified procedure when the pressure drop across an orifice or nozzle is small. We can write HI is CP0 const PE let delta P and delta T be the decrease in pressure and the temperature across the nozzle. Since we are considering reversible adiabatic flow, we can note that we have reversible adiabatic TE on TI, PE on PI, Ti minus delta T, Ti and using the binomial expansion on the right hand side of the equation, we can write this relation. If delta P on PI is small, delta T on TI delta P on PI. Substituting this into the first law equation, we can obtain VE CP0 delta P Ti on Pi. But for ideal gas, we have CP0 Kr and Pi R Ti on Pi. Substituting, we can obtain the final relation for orifice which is the same as equation expressed before. Therefore, when the pressure drop across a nozzle or orifice is small, the flow can be calculated with high accuracy but assuming incompressible flow. The pitot tube is an important instrument for measuring the velocity of fluid. In calculating the flow with a pitot tube, it is assumed that the fluid is decelerated isentropically. Assumed that in front of the pitot tube. Therefore, the stagnation pressure of the free stream can be measured. Applying the first law to this process, we can write H if we assume incompressible flow for this isentropic process. Isentropic and incompressible. We can write this relation. T equals TdS V2 on if we consider the compressible flow, of an ideal gas, with a specific heat constant, the velocity can be found as this relation V or equals to this picture shows the pitot tube instrument. It is of interest. Now the error introducing by assuming incompressible flow and using pitot tube. The error by assuming the incompressible flow. Then using the pitot tube to measure the velocity of the ideal gas, today we have P0 What? Or we can write this relation C V2 substituting to the previous equation, we can write this relation. And P0, P on P0 or rearranging, we can write the appropriate relation for an orifice, a pitot tube for incompressible flow. The corresponding equation for the compressible flow and for the incompressible flow Therefore, the second term on the right-hand side of this equation represents the error involved if incompressible flow is assumed. The error is pressure for a given velocity, and the error in the velocity for a given pressure that would result from assuming is an irreversible incompressible flow, the error for incompressible flow. Are also given in table 72. This is the end of this section.